Okay, so today we will go over limit theorem for sequences. So, okay, so first off, it's the nice thing about sequences that converge is, let me write convergent. Convergent sequences are bounded. And you don't need to know the proof, but let me just say, you should know the idea, yeah? Like I guess, limit gets, let me say, takes care of infinite part, care of infinite part, and then for finite part, right, just take max. So the idea is, so like assume limit n goes to infinity Sn, it converges to some number s, then it doesn't matter what epsilon I choose, let's just let epsilon be 1. Then since it converges, there exists n such that for n bigger than n, Sn minus s is less than 1. So we see here that Sn is bounded by s plus 1, right? Or 1 plus s, if you like, for n bigger than n, right? So this is the infinite part, what I'm talking about, because there's infinitely many numbers bigger than n, right? And then you ask, what about the numbers less than n, less than or equal to n? Well, just take the max, right? Because there's finitely many, right? I don't care what capital N is. All I know is that there's finitely not many like positive numbers like less than or equal to n, right? So we see that Sn is bounded by just, if you just take the maximum of s plus 1 and s1, s2, s3, all the way to Sn, right? So the problem was if we just tried to take the max, there's of the whole sequence, the max of like an infinite sequence could be infinite, right? So, but the max of a finite set of numbers is finite. So, yeah, okay. Let's continue. So obviously all your regular limit theorems hold. So for K and R, if Sn goes to S, then Ksn goes to Ks, right? By goes to, I mean like limit, right? So, and similarly, assume Sn goes to S, Tn goes to T, then we have the usual thing, right? This goes to S plus T, and Sn Tn goes to St. Now, the last part is a bit more controversial. Sn goes to S. And if Sn is not 0, S is not 0, then 1 over Sn goes to 1 over S. So obviously we need those conditions or else we will be dividing by 0, right? So, okay. Any questions so far? Okay. So let's see what it means to, what does it mean for limit n goes to infinity Sn to be plus minus infinity, right? So this means if you just think of it as numbers, this means that our sequence gets really big or really small. So another way to write this is, well, if and only if for all m bigger than 0, there exists n such that for n bigger than n, Sn's bigger than m, right? So it means like no matter what, number m I choose, you should think of m as really large in this case. I could find some capital N such that every term after it's bigger than it, right? And since m is, any arbitrary big number, and eventually I'm always bigger than it, I'm gonna go to infinity, right? So, and then similarly, if and only if, so here we take m less than 0, right? Because we want to go to negative infinity, such that for n bigger than n, I want to be smaller than it, right? So to go to negative infinity, like given any like really small negative number, like negative 1 million, right? I could find some capital N such that after it, I'm smaller than it. Okay. Any questions with the definition? So for again, I guess the reason we use M is because we normally think of like epsilon as small. So here, like we think of like capital M as like, really big in like absolute value, right? Negative 1 million is still really big in absolute value. So like, I guess that's why they changed from like M to like, from epsilon to M. Okay. Any questions so far? That's really it for that session. So we're going to move on to questions now. Okay. So let's do 9.4 first. Yeah, S1 is 1, Sn plus 1 is S root Sn plus 1. So 4. So we have S1 is 1, Sn plus 1 is root Sn plus 1. So this is what we call a recursive sequence, right? Because basically recursive sequence basically means the next term is given by like the previous term. Not exactly, it could be like the previous 2 terms or previous 3 terms, but basically the next term is based on the previous ones. So, just to clarify how this works, like S1 is 1, then S2, right, is S1 plus 1. And so I'm plugging in n equals 1, right? So, which is root, S1 was 1, so, which is root 2, right? And then once you have root 2, you plug it in, right? S3 is S2 plus 1, which is root S2 plus 1, which is root 2 plus 1, right? So this thing is your S3. And then you continue, so on and so forth. Okay. And then dot, 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 right? So let's do part B. So I think part A just asks you for the first 4 terms, right? So you just need S1 to S4. So I trust you can all do that. So part B says, assume Sn converges. So let's just say it converges to S, right? I'm just going to call the limit S. Prove limit is 1/2 1 plus root 5. Okay. So let me do a quick thing. Limits don't really care. Don't really care about finite terms, right? So what I mean is, let's assume sequence, I don't know, I think the book assumes sequence start at S1, right? So Sn is what? S1, S2, S3, S4, right? And we assume this one to S, but I'm saying this thing is, well, n starts at 1, right? So this is just S2, S3, S4, S5, so on and so forth, right? This is S. So basically what I'm saying is, if Sn goes to S, Sn plus 1 still goes to S, right? We're missing one term, but I mean, it doesn't really matter, right? Like for, you know, if you just think of an example, like 1 over n is 1, 1/2, 1/3, 1/4, right? This thing goes to 0, right? If I take out, in this case, first term, right? Take out 1, then we get 1/2, 1/3, 1/4, right? This thing still goes to 0, right? It doesn't matter that I took out the 1. And in fact, you could show that you could take out finitely many in the sequence, and it won't change anything. Because I mean, limits care about what happens when you go to infinity, right? So you don't really care about the first finite terms, right? So basically, since Sn goes to S, Sn plus 1 goes to S, right? We assume that, right? Sn converges to S, so Sn plus 1 goes to S. But now we have this relation, right? So taking limits on both sides. And I think you had a theorem that allows you to move limit inside the root. So this part is just S, right? So this is square root. And this is root S plus 1, right? So here, let's square it. So I get S squared equals S plus 1. Go both, you know, S squared minus S minus 1 is 0. And then your quadratic formula, right? So S equals negative B, so negative 1, 1 plus minus square root. B squared is 1 minus 4 times 1 times negative 1 over 2, right? Okay, so the inside should be 5, right? I hope, yeah. So we need to show it converges to 1 plus root 5 over 2. Okay, we're almost there. We have 1 plus minus root 5 over 2. So what exactly tells me, why is it 1 plus root 5 instead of 1 minus root 5? Does anyone know? Any ideas? So just write. The answer is, so the answer is you take the positive one, but like, you know, the question is why.
Because of the sequence?
What do you mean?
Like,
So
it cannot be a negative number.
exactly, yeah. In this case, you can just say that. The fact S1 was, I mean, the fact was S1 was 1, right? Sorry, right here. So, right, so S1 was 1, so clearly square root's well defined. So, because 1 plus 1 is positive, and if you keep square rooting of positive numbers, you're not going to get a negative number, right? So here, 1 minus root 5 over 2 is like negative, right? And you can't square root numbers and get a negative one, right? So yeah, why is because this is the positive root. Okay, so that concludes that question. Any questions so far? Okay, so exercise 9.6. So x1 is, I'll just write it down. Xn plus 1 is 3xn squared. So let's do one more of these. Right? So A show if a equals limit n goes to infinity xn, then a is 1/3 or a is 0. So basically, it's kind of like the previous question. Assume limit exists, show it's some number, right? And so again, so you should take limit. So the reason I could take limit is because we assume the limit exists, right? And again, if xn goes to a, xn plus 1 still goes to a, right? Xn plus 1 is just you ignore the first term of xn. So this thing is a, this thing is 3a squared, right? Okay, so let's subtract 3a squared minus a is 0. And you get this, right? So a is 0 or 1/3. So that concludes the first question. Okay, so the next question is b, does limit n goes to infinity xn exist? So what do you all think? So basically the question is, can this limit be 0 or 1/3? So why don't we, if you're unsure, let's plug some numbers in, yeah? So let's, scratch work if you're unsure. What are you gonna notice? If I plug in, what is x2? X2 is 3x1 squared, that's 3, is equal to 3x2 squared, that's 3 times 3 squared, that's 27. And you're gonna notice it's gonna get bigger and bigger. So x3 squared, so that's 3 times 27. I'm not gonna calculate this, yeah. But if you try out the first few numbers, you see it's blowing up, right? It's going off to like infinity. So can this so your idea should be it can't go to 0 or 1/3, right? I mean, it's clearly getting bigger and bigger. So if you want to do this, formally, let me just write this. I'll let you all do this because it's like the first day of class problem. You do induction, right? Formally prove if x1 is 1. So this is like the base case. X2 is bigger than 1. Then like inductive step. If xk is I guess then if x2 is bigger than 1, I guess this is actually your base case, then x3 is bigger than 1. And then if xk is bigger than 1, then xk plus 1 is bigger than 1. Right, something like that, yeah. So, but I think it's clear, right? I mean, you're getting bigger and bigger. I put bigger than 1 because it seems the easiest to show. We don't really care what the number is. We just care if you're always bigger than 1, you can't be 0 or 1/3, right? Okay, so what went wrong, right? So that's part C. So what went wrong was, here we assumed the limit existed, right? If the limit existed, then the limit has to be 0 or 1/3. But the point was the limit doesn't exist. So limit did not exist. Right, and hopefully from our calculations here, you can see that the limit should be infinite. you're getting bigger and bigger, right? So, but the question never asked you to prove it was infinite. Just asked you like what went wrong. Okay. Any questions so far? Okay. So let's go over some of the definitions of being infinite. So I'll start off with 9.9. Yeah. So suppose there exists n naught such that Sn is less than or equal to Tn for what? For all n bigger than n naught. So what do we get? So prove if limit Sn is positive infinity, limit Tn is positive infinity. So this will be an example of, practicing the definition of limit being infinity. So suppose there exists n naught such that Sn less than Tn. I think it's less than or equal to, right? So for all n bigger than n naught. A, prove if limit n goes to infinity, Sn is positive infinity, then limit n goes to infinity, Tn is positive infinity. So let me go up really quick and show you, just remind you all what the limit to infinity means. So where was this was the definition, right? Right here. So for all n bigger than 0, there exists n such that for n bigger than n, Sn is bigger than m, right? So I'm just gonna rewrite that. So what do we know? So we want to show first. In this case, is the sequence is Tn. For all m bigger than 0, there exists n such that for n bigger than n, Tn is bigger than m, right? So I need to show this holds for all m bigger than 0, so let's let m be bigger than 0. Now, what do I know? I have this, right? So I have this at my disposal. So we have, since I used m already, for all m1 bigger than 0, there exists n1 such that for n bigger than n1, Sn is bigger than m1, right? So this is just the definition of the limit of Sn being infinite. Okay, so I have the what I just wrote. So basically, let's choose. So I let m be bigger than 0. So I could choose m1 to be my m. Then from here, from what I have, then there exists n1 such that for n bigger than n1, Sn is bigger than m, right? Because m1 is m. So okay, so now my goal is to find the n that works, right? So I'm gonna let n be the n1, and what you'll see is, okay, for n bigger than n, which is n1, we have that this part, the part I just wrote, held, right? But Sn was what? Sn, by assumption, is smaller than or equal to Tn, right? So this is smaller than or equal to Tn. And if you transitive property, Tn is bigger than m, right? So we just showed, and then we're done, right? So hopefully it's not that bad. It's just use definition. Okay, so then I normally don't do the second part of questions, but since the second one is like negative infinity, let's just do it. So I think part B says like if limit n goes to infinity, Tn is negative infinity, then limit n goes to infinity, Sn So I'm doing this just so, everyone gets a taste of what the negative infinity definition is. So let me go back up. So remember, I put in blue, right? Yeah. So we're going to practice using this definition now. So it's, same thing, but like m is smaller and Sn is smaller, right? So we do smaller than and then smaller than. So again, same process, right? Same process as what we have above. So we want to show this part, right? So want to show for all m less than 0, there exists n such that for n bigger than n, Sn is less than m, right? So again, this should always be your first step. And then what do we have? We have this assumption, right? So I'm going to use m1 again, less than 0. There exists n1 such that for n1, Tn is less than m1. So hopefully you all know in this case it's the same thing, right? Let m be m1, then from what we have, there exists n1 such that for n bigger than n1, Tn is less than m, right? Because m is m1. And again, I need to show there exists some n, so I'm going to choose my capital N to be n1. Then for n bigger than n, I have Tn is smaller than this, but I also have from assumption here, I'll put double blue, Tn's bigger than or equal to Sn. So again, by transitive property, Sn is less than m, right? And that is what we wanted to prove. So in this case, it wasn't that bad. It was just your m1 and n1s were just pretty, your n and n1 and m and m1 were just the same. Okay, but just to, everyone get used to the definition. Okay, is everyone clear so far? Okay, so let's do something different. 9.11a, show if limit Sn is plus infinity and the infimum of Tn is bigger than negative infinity, then limit Sn plus Tn is positive infinity. So I'll just do A for you. Show. So we have two things at our disposal. We have the limit Sn is plus infinity, and infimum of Tn is bigger than negative infinity. So before I write anything, what does this mean? So this means well, right? This means this is just some number, right? What letter? Yeah, let's use little m, right? Because what does infimum being negative infinity means? It means your set, if your infimum was equal to negative infinity, it means your set was not bounded below, right? If you're bigger than negative infinity, then you are bounded below. And completeness axiom tells you there is a greatest lower bound. So basically, in other words, we're saying, because infimum can't be infinite, right? So it can only be negative infinity. So here, it's just some number. So show, or want to show, limit n goes to infinity, Sn plus Tn is positive infinity. Okay, so quick thing. So let's write out what we want to show, right? Want to show for all m bigger than 0, there exists n such that for n bigger than n, Sn plus Tn is bigger than m, right? Because my sequence is this thing, right? This is just like the whole sequence. So it's Sn plus Tn. Okay, so again, let's let m be bigger than 0. And we have this, right? At least this part is we have for all m1 bigger than 0, there exists n1 such that for n bigger than n1, Sn is bigger than m1. All right, so here, what should I choose my m1 to be? So I have this, right? So I have this holds for all m1. Now I can make a choice for what m1 is. So any ideas on what m1 should be? I can tell you it's not just m. So if you actually work this out, at least do the scratch work, the correct thing would be let m1 be m minus m, right? So again, lowercase m was the infimum of the tn's, right? So here, why do we do that? So first off, there exists n1 such that for n bigger than n1, Sn is bigger than m minus m, right? So again, let's let n equal, so in this case, n is n1. Then for n bigger than n1, which is equal to n, we have this is true, right? Now let's add m on both sides. So, right, if and only if. Now, m was what? M was the infimum of the tn's, right? So certainly this is true. Right? Because m is infimum, in particular, it's a lower bound. So it's a lower bound of the tn, so any tn is going to be bigger than little m. So I certainly have this direction, and then transitive property. You know, yeah, and that is what we wanted to prove. Yeah. So I mean, so if you ask me why I chose this, it's because I sort of did this scratch work first. but like, yeah, so if you're doing it for the first time, you know, do the scratch work, figure out what m1 should be, and then write it out, right? But I don't think it's that difficult. Most of these are pretty intuitive. Okay, any questions so far? Okay, I'll do one more. So I think that's enough for like the infinite stuff. So let me just go over something cool. So 9.15, limit n goes to infinity, a to the n over n factorial is 0 for all a and r. So so this thing is pretty cool. So let me just, the idea is, I'll let you show this, but the idea is given a and r, right? Let's absolute value of like n factorial is going to be bigger than absolute value of a to the n for n large enough, right? I'll say that. Basically, I mean, factorial grows way faster than, you know, some power. So if you like, let me just say, yes, let me just say this. I want this actually, a plus 1 to the n. The term inside doesn't matter. So for example, n factorial is bigger than 3 to the n, just to convince you all. Like if n is large, right, here, if n is large, let's say n is like 5. Here I'm multiplying 3, how many times? 5 times, right? On right hand side. But on this one, you see most of the numbers are bigger except the first two, right? 4 times 3 times 2 times 1. So basically what you're going to see is, maybe, I haven't checked which one's bigger, but for if you take n large enough, right? This 2 times, yeah, sure, this is bigger than this, but everything afterwards is like gonna blow up, right? So if you take n like large enough, right, you can see this is true. Star. And this, if you want to prove it, so basically what you would do is find the starting point. So find starting point where n factorial is bigger than 3 to the n. So that'll be your base case. So just find some n such that it's true, and then use induction. Right? And the same would hold for like 4 to the n, right? 4 to the n, 5 to the n, it doesn't matter, right? If you go far enough, n factorial is bigger. So if you agree with this, you're gonna get this 0 less than or equal to a to the n. Now this is gonna be true, right? So again, if n factorial is bigger than, I don't even need the equal to, but if this is true, if and only if I flip it, this is true, right? Well, this should be fact, right? So that's how I got this part. In fact, it should. I don't even need the equality sign, but basically you use squeeze theorem. So hopefully you all recall squeeze theorem. So this thing is a over a plus 1 to the n, right? Now this thing, a over a plus 1 is a number between 0 and 1, right? And if you raise a number between 0 and 1 to whatever power, it gets smaller and smaller, right? Like 1/2 squared is 1/4, 1/2 cubed is 1/8, 1/2 to the 4th is 1 over 16, right? So this will go to 0. This will go to 0. So this thing goes to 0. But the cool thing is, what does this mean? So a to the n is like exponential, right? And most people think exponential is super fast. So it turns out n factorial is faster, right? So exponential growth is nothing compared to factorial growth. So factorial growth faster than exponential. And so for people who are interested in how functions grow, the next step is n to the n. So n to the n grows faster than n factorial. But I'll let you think about that. The proof is actually not easier than the one I just did. But yeah. Okay. Actually, that's all I have for today. So again, so let me state the quiz now. So the quiz, what is it? Quiz 3, I think. Yeah, should be quiz 3. So first question. I will give you sequences, so more than one. And then, you tell me whether it converges or diverges. And then the second question would be use like epsilon definition to show like limit of a sequence is some number, right? Right. It's the ones I did last discussion, right? Like maybe show limit n goes to infinity. I don't know. What is there? 2n minus 1, 3n plus 4, right? Is equal to like 2/3, right? So like use the epsilon definition to show this. Okay. Any questions? Oh, there is chat. Okay. Yeah. Okay, that's all I have for today. Thank you.
Do you know when is the midterm?